Hello, everyone. Good afternoon. Welcome to the AI infrastructure and the tool session. This session we will have two talks. One is about optimizer backend optimizer for deep learning computation. Another one is for AI platform. So I'm Jilong Xue from Microsoft Research ASA. So I will start first talk. It's glad to introduce this our recent project called Wolong, a backend optimizer for deep learning computation. In recent years, deep learning has gained many success in the areas such as vision and speech and NLP and so on. Along with this success, there are many emerging innovations. So in one side, the deep learning scientists are continuously inventing new models and workload patterns. For example, beyond the RNCN, the typical models, there are also new workload patterns like GAN, reinforcement learning, and graph neural networks. So in other side, the hardware vendors are actively inventing new accelerators for speed up the computation. For example, beyond the CPU, GPU, and FPGA, there are some more and more new accelerators, ASIC accelerators, and high-speed network links. So within this situation, several deep learning frameworks were proposed. For example, like TensorFlow, CNTK, Computation, for user to easily write a DN program and compute on different hardware devices. Typically, these frameworks abstract deep learning computation as a Dataflow graph. The node is represented to perimeter operators, and the edge represents the tensor data. So using Dataflow graph as a programming IR do get sufficient experience and programming flexibility. However, it also brings the challenge of how to effectively do graph computation over different devices. So we think a systematic way is to leverage a compiler and the optimizer infrastructure to bridge the DL framework and the hardware. This is because compiler can combine both information from application pattern and the hardware feature to make a best match. As it has a global view of the Dataflow graph, so the compiler and optimizer can also do optimize for distributed computation. Thus, such infrastructure is critical for both the training and the inference scenario. Based on this observation, we started a research project 1 year ago. We proposed a system called Wolong, which is an optimizer stack for deep learning computation. The motivation of Wolong is to address deep learning performance optimization problem in a systematic way. Specifically, we're going to leverage the general graph optimization passes and leveraging the principle of software and hardware co-design and just-in-time compiler. The right figure is the architecture of Wolong. Wolong has three optimizer modules. The global optimizer, local optimizer, and tensor placement optimizer. So the global optimizer has a global view of the computation graph and conducts distributed optimization through graph partitioning and leverage the hardware features. And the local optimizer mainly optimizes the subgraph after the graph partitioning for a specific device using the JIT compiler. And the tensor placement optimizer mainly optimizes for tensor layout and placement. All these optimizations in Wolong are designed in an automatic and transparent way. So the Wolong generally target to optimize the communication and execution and the memory efficiencies. So first, let's look at a case of global optimizer. The subtitle is Fast Distributed Deep Learning Computation over RDMA. As I introduced before, a deep learning computation is modeled as a Dataflow graph. To execute a Dataflow graph in distributed servers, so the DL framework first needs to partition the graph and dispatch each subgraph to corresponding servers. After partitioning, if there is an edge go across two servers, we need to insert a pair of send and receive nodes. So this pair of nodes are responsible for real data transformation during the computation. worth to mention, this kind of mechanism is general to express both the model parallelism and the data parallelism pattern, which are a common way to scale deep learning computation in distributed servers. In such a general framework, the communication has to leverage a general communication library. However, in most deep learning scenarios, the tensor transformation in such a framework brings significant overhead, which becomes a major bottleneck for scalability. To demonstrate this, we use a simple micro benchmark. We just send a tensor with different size from one server to another server. This figure measures the latency of the different tensor size. As we can see, even use the same network, there is up to 10x latency gap between the general RPC library and a well-optimized program, which carefully leverages RDMA. So to understand the overhead of RPC, let's go to a little bit more details. We observed that the major overhead of RPC is caused by memory copy, and it is inherently unavoidable for such a general library. This is because the general RPC is designed for dynamic data structure, and it lacks of knowledge about the actual data placement and the message size. As illustrated in the right figure, a message sent from sender from sender has to be first copied from application memory to the RPC managed memory, and then serialized into a larger buffer to better leverage the batch efficiency. Correspondingly, deserialization and memory copy also happened in the receiver side. To address this overhead, we cannot leverage such a general library. Instead, we should use a right-time optimizer, which can dynamically decide the memory placement according to a specific computation workload and the network topology to completely remove the memory overhead. Thus, in our distributed graph optimization, we combine both the properties of computation graph and the RDMA network feature. First, for the tensor structure, unlike the general message type, the tensor data in deep learning computation has several special properties. First, it consists of a plain byte array with sufficiently large size, often from several kilobyte to megabyte. Due to this, we actually do not require data serialization and deserialization in this kind of transformation. Due to access pattern of tensor is already sequential, we also do not require extra batching. But all this information can only be decided in the right time. So second, with the RDMA hardware and the protocol, we can manage both the local and distributed memory in a unified view. We can do efficient memory copy between host memory through the one-side RDMA and the read and write primitives, and efficient memory copy between device memory to host memory with the GPU direct RDMA. Thus, a global graph optimizer for distributed computation is a systematic way to address scalability of the framework. This is because first, global optimizer can have the entire view of and the control of the memory placement among the device and servers. Second, it is capable of making global optimized strategy for tensor data placement in the right time. So based on these observations, we designed a new communication mechanism in our optimizer for distributed computation over RDMA. In this mechanism, it has two phases, the graph analyzing phase and the graph execution phase. First, before the graph is real executed, there is a graph analyzing phase. In the sender side, our optimizer first detects physical memory address of the sending tensor and tells the information to the tensor manager to reallocate it as the RDMA compatible memory. So this can dynamically avoid the memory copy in the sender side. Similarly, in the receiver side, through graph analyzing, we can know the receiving tensor side beforehand. So we can pre-allocate the receiving tensor as RDMA compatible memory to avoid the receiver side memory copy overhead. So after the graph analyzing phase, in the execution phase, when the sender node is ready to send the source tensor, it can just issue a one-side RDMA write command. And the RDMA NIC will directly copy the source tensor to test the tensor's memory. In the receiver side, since the RDMA didn't have the notification mechanism, so the receiver operator will continuously pulling a flag byte until the value turns to 1, which means the whole tensor data has already arrived. So it can just simply pass the reference of the tensor to the downside operators. As we can see, this communication mechanism in our optimizer, we can completely remove the memory copy overhead in the both sender side and the receiver side, and most importantly, without affecting the usability. So this is a performance evaluation for our optimized communication mechanism on both deep learning frameworks and the real training workload. So our experiments are conducted in a cluster with 8 servers. To evaluate the performance, we implement our optimizer in TensorFlow. The left figure shows the training throughput of TensorFlow and our optimizer version on a set of deep learning benchmarks, including RN, CN, and fully connected work. As we can see, with our transparent optimization, in same hardware environment, the performance can be improved from 1.8 times to 8.1 times. We also demonstrated the benefit on an end-to-end sequence-to-sequence translation model using public datasets, which is shown in the right figure. The y-axis is perplexity, which measures the convergence quality. The lower the better, and the axis is the training time. As we can see with optimization, the convergence can be speeded up by 2 to 3 times. So after demonstrating the benefit of our global optimizer for distributed deep learning computation, now let's look at a case of a local optimizer. So we are mainly talking about the kernel fusion for deep learning on GPU. The local optimizer is mainly optimizing a subgraph on a specific device. Currently, we mainly target to GPU. So as I introduced before, deep learning framework often model the DN computation as a graph of operators. Using graph has several advantages. First, it has good expressivity and to represent arbitrary neural network structure through just composing the graph with the primitive operators. Second, it is flexible to run the graph on multiple devices or multiple servers through just different graph partitioning strategies. However, this flexibility comes with a significant overhead. Since the typical DN model contains thousands, even more operators, scheduling overhead is a major bottleneck for the computation. So to schedule this overhead, we'll introduce the overhead like kernel launch overhead and the cross-operator communication overhead. And also, since the primitive operator is too fine-grained, it is hard to leverage vendor's library for a specific computation workload. To demonstrate this, we compared the execution time of a 80-step LSTM model in TensorFlow and cuDN. cuDN is a vendor-provided library from NVIDIA. In TensorFlow, this model is constructed by about 1,600 operators. And the framework has to schedule all the operators in the subgraph during the computation. However, in cuDN, since it is highly optimized for removing the scheduling overhead, it can give an order of magnitude performance improvements for the same workload. We also try to manually fuse all the kernels into one CUDA kernel. It shows we can get similar performance with the cuDN. So now let's have a high-level comparison of the deep learning frameworks and the hardware-specific library in terms of programming flexibility and the computation efficiency. And see the general challenge of in current DL frameworks. First, the deep learning frameworks like TensorFlow, PyTorch, and the CNTK has designed for users to easily program their deep DN models. And thus, they mostly embrace the flexibility and expressivity through using the graph operators to model computation. But they target less about the performance extreme performance optimizations. The other side, the DN libraries are designed by hardware vendors to push the extreme performance boundary. However, due to they are mostly hand-tuned and highly optimized for a specific submodule, so it is impossible to handle customized or new network structure, which means they have good efficiency but poor flexibility to support arbitrary model. Thus, if we have a compiler that can dynamically generate a library-like code in the right time based on input data flow graph for deep learning frameworks, we can get both the flexibility of DR framework and the computation efficiency. So under this situation, we propose the compiler stack for optimizing deep learning computation, so-called Wolong. Wolong compiler takes input as a computation graph, and it has two optimization layers. The graph level optimizer and the target specific JIT compiler. The graph level optimizer applies a set of target independent graph optimization passes through graph rewriting. So commonly such as CSE, constant folding, and so on. So a special optimization in this layer is operator batching, which can automatically batch the same type of operators to better leverage the batch efficiency, which I will introduce this later. The second layer is the target-specific JIT compiler, which can fuse and compile a subgraph into an efficient kernel. Currently, we mainly target to GPU device. The optimization in this optimizer include static shape inference and type inference and static memory planning and aggressive kernel fusion. So here is this is the general execution flow of Wolong compiler. The graph level optimizer works before the graph execution, and the JIT compiler works during the execution. First, in the graph level optimizer, when getting an input graph, it first detects some subgraph that can apply optimizations. For example, if the graph contains several same type operators, the operator batching path will automatically merge these operators into a larger one through graph rewriting. So after the graph optimization, we start to do real execution. For a subgraph that is the first time to be executed, our compiler will conduct a shape inference and a type inference for this subgraph, as well as a static memory planning process based on the graph and the GPU features. After that, we automatically generate a fused kernel code for the whole subgraph, and use a JIT compiler to compile the code into a new kernel. Finally, we replace the original operators in the subgraph with this new compiled kernel, and then execute it. So in later iterations, if the graph and the input shapes has never been changed, it will hit the catch and directly execute from pre-compiled kernel. Since we dynamically fused all the operators of the subgraph into a single kernel, it can remove all the scheduling overhead. In the following slides, I will introduce a case of operator batching and the details of a JIT compiler. So first, let's look at how the operator batching in graph level optimizer works. Here we introduce the case of matrix multiplication merging. As we know, matrix multiplication is a very common operator in DN workloads. It has mathematical equivalent rules. If two mathematical operators shares one same input tensor, we can concatenate the other inputs to merge these two mathematical as a larger one. The outputs of the merged mathematical is equivalent to the concatenation of the outputs of the two original mathematical operators. Based on this rule, we can actually automatically detect this pattern in our optimizer and rewrite the graph through insert, concact, and the split operator to merge the mathematical, to automatically merge the mathematical operators. So after graph rewriting, we can do further optimizations. So our tensor placement optimizer will get this information, and it will track this input tensor and allocate them in a physically continuously placed memory, so that the concact operator can avoid the memory copy during its computation, as illustrated in the right figure. With such kind of graph level rewriting optimization and memory placement optimization, we can transparently optimize the graph for better performance. So after the graph optimization, let's move to the JIT compiler part after, move to the JIT compiler part. So in this talk, we mainly focus on how to do the kernel fusion in our JIT compiler. Compared with the other optimization frameworks, our goal is to conduct a very aggressive kernel fusion. Ideally, we would like to fuse the whole subgraph into a single kernel to completely remove scheduling overhead. First, let's start from element-wise kernel fusion. This type of operators includes binary operators like the AND, sub, multiply, divide, and so on, and the unary operators like sigmoid, ReLU, and so on. For example, if we want to compute a sigmoid of x1 plus x2, the computation graph constructed by DL framework will contain two element operators, the AND and the sigmoid operator, and so in the left figure. So the right figure is the corresponding element-wise data dependency graph. As we can see, for element-wise operator, there is no cross-element dependency for this computation. So we can simply assign the computation for each element to a single GPU thread and leverage the on-chip register memory to share their intermediate results. So for this kind of workload, the generated code look like in the figure. It's relatively trivial. Since the fusion element-wise kernel is relatively simple, so many other compilers currently also support this kind of fusion. However, fusion just the element-wise operator, we think is not enough, because the element-wise operator only occupies a very small fraction of all the operator sets. Thus, our goal is to do aggressive kernel fusion to fuse arbitrary operators. To support arbitrary kernel fusion, there are some challenges need to address. First, unlike the element-wise operator, two non-element-wise operator often has cross-data element dependencies. We have to carefully control the dependency for each computing thread. Second, grid-level global synchronization is a critical parameter for such kind of workload fusion. However, current GPU architecture has fundamental challenge to support general global synchronization. Third, some communication between operator has to rely on the device memory, which may increase the memory usage. We have to carefully optimize the memory usage and the buffer allocation. To get better understand, let's look at an example of fusion to continuous memory metamor operator. Since each thread of the second metamor has to read almost all the data element from other thread of the first metamor, so a realistic way to do the fusion is to store the results first metamor into device memory, and the second metamor can directly read the inputs from the intermediate buffer. So the right figure is a pseudocode for this kind of fusion. We can see we insert a global barrier between the two metamor function call. So however, the fact is in GPU architecture, this kind of code is really challenging to run. So to understand why the challenge happened for GPU architecture, so to first we need to understand let's look at how the current DL frameworks schedule a Dataflow graph in GPU. So typically, the DL framework uses CPU to schedule operators, and the GPU is responsible for executing each operator's kernel. So the GPU often consists of several stream processors, which can concurrently execute the block task of the GPU kernel. Let's say there is a graph with only two operators, metamor and convolution. So the convolution need to read the result of metamor. To run this graph in GPU, the DL framework has to schedule these two operators one by one. For each operator, we need to explicitly split it as multiple block tasks according to the data size, and schedule them on GPU to multiple GPU stream processors. Due to limited number of stream processors, the blocks has to be implicitly executed in several batches, like this. So then the second operator is scheduled in the similar way. As I mentioned before, if the graph contains a lot of operators, the kernel launching and the operator scheduling will become a significant overhead. So a straightforward way to remove this overhead is fusing all the operators of subgraph into a single GPU kernel. For example, if we want to fuse the metamal and the convolution operator into a single kernel, so we can compose them as two stages. The first stage do the metamal, and the second stage do the convolution. So correspondingly, all the block tasks also include the two stages. However, since this two kernel has cross-thread data dependencies, we have to insert a barrier between the two stages in the kernel. So for all the blocks, they also has so each block has to enter a global barrier. However, as I mentioned before, due to limited SM resources, only the first several blocks of the kernel were real as scheduled. They will be blocked in waiting for barrier. So as GPU has no block context switch, the later several blocks will never be scheduled. So this kernel will fail to execute. So to address these issues, we propose to use the persistent thread and the virtual block mechanism. To fuse the same two operators into a single kernel, we first limited the number of physical blocks of the fused kernel according to the available resources, so that all the blocks can be executed concurrently. Then we treat the original blocks of each operator as a virtual block and assign them to physical blocks in a round-robin way. We implement this through remapping their block ID in the code generation time. Then we are free to insert a barrier between the two stages of virtual blocks, since all the physical blocks are already active. With this mechanism, we can fuse all the kernel into a single GPU, as long as we can generate each operator's source code. So till now, to fuse multiple operators, we are actually generating a static sequence of code for each operator. For example, for the left Dataflow graph with 3 operators, they will be sequentially assigned to physical blocks, like this. However, since the sigmoid, let's see the graph, since the sigmoid operator and the AND operator are small operators, and they have no data dependencies. So if we use the current DR framework, they can leverage the data parallelization. So in our fusion framework, there is some underutilization for GPU resources. To further push the resource usage, we support kernel packing mechanism, which can pack the small kernels into a more compact way during the virtual block assignment. So we can pack the AND operator into the sigmoid operator's batch. In this way, we can explore the graph level parallelize and remove kernel launch overhead in the same time. Okay, so this is the way of how to fuse the kernel code in our compiler. Basically, we first need to register, for each operator, we need to register its kernel source code and some other meta information into our code generator. We can only fuse the operator that has been registered. For arbitrary graph to be fused, we first conduct a shape inference and the memory place planning pass, and then generate the function calls for each operators. For example, for this graph, we can first generate the sigmoid, and then the metamal, and the final is for the ReLU operators, in this way. So during the process, we will automatically insert a barrier when needed and the packing kernel if possible. Currently, we already support a lot of operators. We are still and more into the framework. So now let's look at a preliminary performance gain of kernel fusion. For the R inference benchmark with 80 steps LSTM, as we saw in the beginning, currently our compiler can automatically fuse and compile the whole graph with 1,600 operators into a single GPU kernel. The right figure demonstrates the performance comparison with original TensorFlow. The bar with the title OP batch means we only apply the operator batching optimizations in the graph level optimizations. And the fusion bar is the final result of kernel fusion. We can see with our compiler, we can get about a 10x speed up for this workload. So in conclusion, we think compiler infrastructure is critical for both cloud and edge AI because it can automatically and transparently optimize both the distributed training and the local inference on different devices. And we also think system innovation is the key to bridge the application and the diverse hardware. Since the current framework already abstract common IR, which means the Dataflow graph IR. And we can leverage this to co-design software and hardware for extreme efficiency. We also have developed the Wolong prototype to demonstrate the initial improvements. It's up to 8 times speed up for training and 10x speed up on the inference workload. Thank you. That's my talk. So do you have a question?
What's the relationship with Wolong and Pi?
Wait, here's a, sorry.
Okay. There are the 2 projects?
Yeah, it's 2 projects, but it can integrate into same platform because Wolong is mostly targeted to the framework. So computation framework, and the Pi is targeted to how to schedule a job to the different servers. So after Pi scheduling into a specific servers or GPUs, so Wolong can apply the optimization. So it can be integrated into a same platform, but 2 different systems.
Okay, so why 2?
You can treat them as 2 modules in a same system.
2 modules?
Yeah, but actually it's to this different system.
Okay.
Thank you.
Oh, wait, hold on. Wait, hold on here. Thank you.
So the global optimizer part is for mostly for multiple servers, and the local optimizer is for just a single server.
Thank you.
Thank you.
So when you're applying this technology to the parameter server, just for example, so do you do any compression on the traffic between the nodes and also the IPS?
So yeah, currently we are not applying the compression stuff in this work, but the compression is, I think the technique of compression is orthogonal to this techniques, so we can also apply the compression into the transformation. It can further reduce the communication overhead. Yeah, thank you. Okay, if there's no other question, let's welcome to the next speaker. Thank you.
Good afternoon. My name is Fan Yang from Systems Research Group, MS Microsoft Research Asia. And today I'm going to introduce OpenPAI, the open source initiative for AI platform in China. So here's the background. So we all know that AI becomes one of the major focus and a very heated topic across academia and industries. And we believe that there exists major opportunities to democratize AI through the innovations on AI infrastructure that can lower the bar for newcomers to facilitate AI education and to speed up the AI research. And also that could potentially help accelerate the penetration of AI technologies across industries, especially for the traditional industries. So we feel that the current status of the AI platform is still in early stage. We find that there exist ad hoc ways to build and deploy an AI platform. It's relatively easy to build small-scale platforms with narrowed specific purpose. But we actually need, to help the entire industry, we actually need a platform that works in different environment and application scenarios that include the on-premise, cloud, and even hybrid hosted environment. And also the AI platform not only can support domain-specific application like image, video, speech, language, but also they need to support them all in one platform, and also for the AI applications in a certain vertical domain. And this AI platform need to be highly compatible, need to be extensible. It has a very good manageability and efficiency. So before I dig into the details, I need to emphasize again the importance of the AI platform. The AI platform actually provide the infrastructure support for the advance of the AI technologies. It actually support the deep learning algorithms and frameworks, and the AI platform also should manage hardware in an easy way. A good platform can boost the innovation and the productivity of different kind of AI research field. It allows the researchers and the AI practitioners to focus on the innovation itself instead of the hassles of infrastructure construction, deployment, management, and optimization. And a good AI platform could enable result sharing. A good platform can help build a community for mutual knowledge sharing, and to help each other to leverage the previous research result, and thus can speed up the innovation. So an open platform for AI R&D and education is actually, we feel that it actually helped the co-development of AI innovation, education, and the platform evolution. So a good platform, we can leverage this platform to design the AI course project, to perform training, to grow the AI talent pool. And also, an open source, the platform can help to encourage the resource sharing and for collaborative innovation. So here is the overview of the AI platform that in my mind. The underlying infrastructure layer, including hardware and the various of deep learning technology we have already built. And upon that, we need a management layer to manage the heterogeneous cluster for resource management and scheduling. And we also, as Jilong mentioned, that we also need a platform to host the system-level intelligence and optimization. And also, we could have that platform to support the deep learning and the intelligence exploration. And based upon the platform, you can build a shared resource for practice or for education. And also, the platform can potentially host the labeled deep learning data. And also, you can leverage the platform to, and also leverage the tools for management integration and AI lifecycle management, or also compiler optimization. The cognitive capability built on the platform, including natural language understanding, visual perception, speech recognition, as I mentioned, across different domain. Let me focus on the middle layer, the platform to manage the heterogeneous cluster. So we open sourced a PI called OpenPAI, a platform for AI. So this platform is GPU cluster management infrastructure. It has the following features. First, it's open. So it's open source. It's licensed under MIT license. And it's actually operated in the open collaboration model. We actually work with various of partners. I will mention the details later, and to develop and evolve the platform together. And the OpenPAI is actually extensible. It not only support all the major deep learning frameworks, it also, extensible to support a new workload. It also supports diversified hardware, including FPGA, GPU, and ASIC, given that the drivers are available. And OpenPAI has it has a modular design, so it actually embraced the microservice design paradigm. So every service run in a container. So this microservice choice can help us replace a certain component, PI component, very easily. For example, if you would like to have try a different storage option, you can switch from, for example, HDFS to GlusterFS. And PI also have a good efficiency. It supports very fine-grained GPU scheduling. It also supports high-speed network, including RDMA, etc., etc. PI also has a relatively good manageability. It actually provides a web UI for platform operator to manage and monitor the platform. It also help the deep learning user to manage job, submission job, or even monitor the hardware utilization. And PI provides some fault tolerance capability, so you don't have to worry about the failure. And also, PI learns a lot from Microsoft's internal practice. So we actually reproduce the production environment and the realistic industrial usage case for a deep learning model training scenario. Here is a high-level overview of the OpenPAI architecture. The underlying is the host environment that including cloud, private cloud, or on-premise cluster that are running on top of heterogeneous hardware, GPU, CPU, FPGA, RDMA, etc., etc. And on top of that, we leverage Docker and Kubernetes to perform container orchestration, and we provide tools for to deploy the platform easily, and also to upgrade and maintenance. And also we have job management, resource management, etc., etc. So one of the key things in our market as RED is that we try to provide a standardized interface to the deep learning workload and to the platform management tools, so that as long as the interface are standardized, all the deep learning workload or even big data, traditional big data workload can leverage this standardized API to run on this OpenPAI platform. And this would ensure the portability of the workload, meaning that once you successfully run a deep learning job in one PI cluster instance, it can applied to, running on other Pi deployment as well. And also, this interface and the runtime support enable the innovation of higher level AI service like AutoML, etc., etc. And here is a little bit more details of our current implementation. For example, as I mentioned, I use Docker. We use Kubernetes for cluster management. And on top of that, for storage, our current storage option is HDFS because that is one of the most popular distributed storage solution. And we use Hadoop with our own extension of GPU support for complicated GPU scheduling as well as multi-tenancy support. And we now support all deep learning workload and some of the big data workload like Spark. And we are also developing our own AutoML algorithms and the platforms that I will mention that briefly later on. So with this platform, we believe we can build an open ecosystem. So our initial engagement with China AI community is to have a community to, with the AI platform, we can have a lot of shared resource and tools and build the cognitive ability so that we can help in research, in AI education as well as growth, the talent pool. Microsoft Research Asia now work with 4 major Chinese universities to have a China Open AI Platform Alliance. Those 4 universities, including Peking Universities, Chinese University of Science and Technology of China, and Xi'an Jiaotong University, and Zhejiang University. And I would like to provide one case study for the schools of information science and technology of USTC. This is their previous practice. They have 300 AI researchers and students with approximately 400 GPU, and their current pain point is major about operation overhead because that those are AI scientists. They are not infrastructure assistant researchers or IT professionals. So they feel that to operate on a relatively large-scale GPU cluster, it's a lot of work. And for each students and the researchers to run a certain deep learning workload on the cluster require a lot of work. You need to make sure your version is correct. For example, you have to have the right version of TensorFlow, etc., and you have to be careful not to screw up other people's environment, like the correct version of cuDNN, even GPU driver or something like that. And as a result, that the previous cluster utilization is relatively low. So with the OpenPAI deployment, we have, as I mentioned before, we have a web UI interface to help to monitor and manage the GPU cluster, and we actually lower the learning curve for the AI researchers to run deep learning workload. The research result can share across team with Docker image and the job configuration files that require different kind of resource, like, for example, number of GPUs for the job. And the new user, like a new student, when they try to learn, try to run some workload, they can just jump start with some pre-built Docker images. And their GPU cluster utilization improved with our scheduler mechanisms. And they they leverage the platform and run their workload, and we are happy to see that the OpenPAI platform can help them win some of the top and prestigious award in CVPR. So, to summarize, a platform, OpenPAI is actually a platform for AI innovation. It provided a much needed playground for AI research and development. Pi actually is represent a class of realistic and production environment where AI research should target at, because that, as I mentioned before, Microsoft internal production environment is very much like OpenPAI. And it has a free platform for non-professionals. By non-professional, I mean IT professionals or system researcher. So we have a relatively low operation overhead, and we provide web UI-based job management tools so that AI researchers can easily use the platform to run their AI workload. And so the researchers can focus on AI research itself instead of tedious IT stuff. And with the platform, we can help the result sharing and reproduce the research result. As you might know that it's very hard for AI researchers to reproduce other people's workload, because that they often require a lot of parameter tuning. So our platform can help you with a Docker image that include all the parameter you set for the paper you published. And also, the platform can help the system research itself. Here I would like to give a few examples of the research opportunities systems group are working on. For example, we are trying to exploit to understand what is the right system primitive for deep learning scheduling in a large-scale GPU scheduling. For example, in the big data era, big data jobs are expressed with MapReduce task, and later on they usually have a DAG scheduling. But before the big data era, if you look at the distributed process, they usually the scheduling primitive is usually time sharing, migration, etc., etc. So what is the right primitive for deep learning workload? It's one of our research focus. And also that we feel that because deep learning workload usually require large data and larger neural model size so as to have a relatively good accuracy. So we feel that how to manage GPU memory more efficiently is one of the potential opportunities we can exploit. For example, we can leverage a very traditional system concept like a virtual memory and some of the technology like memory compression, etc., to optimize the GPU management during deep learning model training. and we have identified several cases where certain deep learning technology like the AutoML algorithms may have some very subtle interplay with the underlying system's cluster scheduling. How to optimize those deep learning job that can, target for achieving the good model, having a good model, neural model, instead of only speed up one specific deep learning training session. It's one of the interesting research topic. And also like cross-job optimization and how to identify fairness in the case of deep learning workload, especially for the GPU. Those are very interesting research opportunities that the system research itself can help. So to conclude, we have a platform that can facilitate the research on artificial intelligence. It provides an efficient and ease of use AI infrastructure that can help to put the AI research into practice. And the platform itself is open in the open collaboration model. We actually developed the platform with the university together, and we have an open community. We start from China then, and we certainly welcome university and the researchers or even industry, the practitioners across the worldwide to join us to develop the platform together. Okay, thank you. So after that, I would like to spend a few slides to introduce another piece of work our team is working on, which is called the neural network intelligence. So here is, I would like to show just a few slides. Here is the overall the overall process of the deep learning developers' daily practice. So first, they usually can mine or search some code for a certain deep learning neural model practice from GitHub or related website. And our neural network intelligence platform can index those popular code and neural models and recommend this neural network model or architecture to the user. And neural network intelligence also provide a lightweight open source package for user to run their own training sessions to find a good neural model. And finally, we have visualized tools to edit, search, and debug the neural network model in terms during the AutoML training session. We know that the traditional AutoML algorithm has been developed from a simple hyperparameter tuning to more advanced neural architecture search, including, for example, evolutionary-based search, reinforced learning-based search, or other more advanced technology. And later on, we have seen that people are starting to apply neural evolution or transfer learning in this kind of neural architecture search. So our NNI package actually supports all this kind of technology. And also, we provide a markup language for search space specification. For example, those markup showed in orange, it's a way for user to specify their choice during the search space. So we feel that using a markup language actually provide deep learning researcher a very handy tools to specify a certain neural architecture search. Okay, so we are going to open source this package in maybe 1 or 2 months, depending on the legal process we are going through. We hope that in the future people will use this NNI package to apply a certain AutoML research, so we can enable the more rapid innovation in the AutoML research itself. Okay, so that's all for our talk. Thank you. Any questions? Yes.
So I'm interested in the AutoML part. So could you tell me more about like what kind of AutoML functionality do you support, and what's the usage or consumption from the customer? And is it quickly growing feature and so on? Yeah.
So we decide to open source the NNI as a lightweight package. So if you only have one GPU server, you can use it. If you have, for example, 10 GPU servers, you can use it. And if you happen to have hundreds or thousands of GPU clusters that managed by OpenPAI, you can also use it. So it's quite flexible. And so the platform, the package itself does include a certain typical or classic AutoML algorithm, for example, a random search, grid search, or Bayes method. But we also provide interface, standardized interface, allowing deep learning researchers to develop their own AutoML algorithm, which is actually one of the active research topic right now. And so this is one of the target customers we try to support, innovator, AI innovator. The other part of the customer is that some of the people actually do not have too much knowledge on deep learning itself, and they would like to have, for example, try some CNN model. But in order to better leverage the CNN model, they have to do some fine tune. For example, one of the very typical training practice is to retrain only the last few layers of the CNN model so as to have a better classification result. Then we have these tools that can help you automatically. You don't have to do anything. You have just leveraged some of the pre-configured package. So this is just like a Microsoft custom vision or Google's AutoML, except that you can run the entire package open source and on your own cluster, so you can play with. You don't have to be forced to log into any cloud offering, right? I hope that addressed some of the question.
Thank you.
We do not support the FPGA yet. Our design actually taking FPGA into account, but we need to verify that with the driver. So I assume that if the driver doesn't have any problem, then we don't have any problem, because that we treat a GPU as just one specified coprocessor, and the FPGA is no different than that. Okay, thank you.